Welcome to the Distant Curve Remote Area Severe Weather Analysis for Broome. I'm your host, and today we are diving into the atmospheric setup for Friday, December 26, 2025. The morning sounding at 10 a.m. local time reveals a fascinating story of tropical instability and wind shear working together. If you find this analysis helpful, please like and subscribe to support continued severe weather analysis. Let's start with the morning sounding here in Broome. Looking at the Skew-T diagram, we can see some impressive energy already present. The most unstable parcel shows roughly 5,100 joules per kilogram of surface-based CAPE. That's substantial energy coiled like a spring in the lower atmosphere. The mixed layer CAPE sits around 2,400 joules per kilogram, which is also respectable. Now here's what's really important. The red and pink shaded area on the right side of the diagram shows that CAPE, that's the fuel for storm development. The environment is warm and moist, with surface temperatures at 31.8 degrees Celsius and dew points around 26.5 degrees. The cloud base is quite low at 685 meters above ground level, meaning storms that form could have strong low-level rotation potential. The wind shear in the lower 6 kilometers is moderate at 7.2 meters per second. We are also looking at a high downdraft CAPE of 1,600 joules per kilogram, suggesting that if storms develop, they could produce intense microbursts, those sudden powerful downward wind bursts that cause severe damage. Now as we move into the afternoon, the atmosphere continues to organize. The surface-based CAPE remains essentially the same at 5,100 joules per kilogram, but notice how the parcel path evolution shows the system maintaining its explosive potential. The stability profile suggests very little change from morning to afternoon. The environment is already so unstable that additional heating has minimal impact on the overall picture. The most unstable CAPE stays around 5,100 joules per kilogram. What's critical here is understanding the threat potential. With shear values below 10 meters per second in the 0 to 3 kilometer layer, we are looking at what meteorologists call pulse storms or multicells, clusters of storms that can still produce severe wind gusts and large hail, but they lack the rotation characteristics needed for organized supercells. The discriminant index, a measure of severe thunderstorm potential calculated by combining CAPE and shear, reaches about 140,000, which exceeds the Australian threshold for significant storm potential. The SHIP index of 2.2 indicates hail potential, though the relatively low shear limits the organized severe threat. Let's examine the wind profile and hodograph. The hodograph, that's the curved plot showing how wind changes with height, displays a relatively modest shear vector. The right mover star, which indicates where supercells would travel if they develop, points toward the northeast. The magnitude of the wind shear is the critical factor here. With 0 to 6 kilometer shear of only 7.2 meters per second, we are well below the Australian severe threshold of 15 meters per second. This means any storms that develop would tend to be relatively disorganized, moving with the mean wind rather than maintaining intense rotational structure. The 0 to 1 kilometer shear is particularly low at 1.1 meters per second, which limits the potential for strong low-level rotation. However, if we consider emergency services planning, the moderate CAPE combined with high downdraft CAPE means that while tornado risk is extremely low, the microburst risk warrants attention. The wind gusts from organized downbursts could still reach 70 to 80 kilometers per hour in localized areas, potentially causing damage to power lines and structures. The right mover vector points northeast, so if strong convection develops, it would track in that direction across the Kimberley region. The atmospheric stability profile, represented by the Brunt-Weissaler frequency, tells us much about downdraft and microburst potential. The lower and mid-levels show relatively low buoyancy frequencies, meaning the atmosphere is quite unstable. Parcels can rise freely without much resistance. This instability, combined with the high downdraft CAPE of 1,600 joules per kilogram, creates significant microburst potential. The downdraft CAPE velocity reaches 56.8 meters per second, which translates to extreme downward accelerations if precipitation falls through the subcloud layer. Here's the operational reality. This profile supports intense microbursts capable of producing destructive wind gusts. For emergency services managers, this means positioning resources for rapid response to localized wind damage is prudent. The freezing level sits at 4,867 meters, providing a deep layer of supercooled water where hail can grow, from the 0-degree level down to the minus 40-degree level at upper levels. If strong updrafts develop, hail growth is possible, though the relatively low shear limits the organization needed for very large hail production. The profile also shows elevated dry bulb lapse rates in the boundary layer, meaning dry air aloft can mix downward efficiently, further intensifying downdrafts and potentially creating dry microbursts that could ignite grass fires if thunderstorms pass over dry vegetation. To summarize, Friday, December 26th shows a tropical atmosphere with significant instability and moderate downdraft potential. While the shear environment limits organize severe weather potential, the high Cape and elevated downdraft Cape suggest that if thunderstorms develop, they could produce damaging wind gusts and localize severe weather. Emergency services should monitor the afternoon development, particularly for microbursts and localized wind damage in northern areas. Always consult the Bureau of Meteorology for official forecasts and severe weather warnings. This analysis is provided by Distant Curve Remote Area Telecommunications. If you found this helpful, please like and subscribe to support continued severe weather coverage for remote Australia.